information from my side. The webcast lasts around 45 minutes and is divided into a 30 minutes presentation and a 15 minutes Q&A. As you are all muted, please feel free to send us all your questions by our chat, which you find directly on the bottom of your screen by clicking on the speech balloon. We're happy to answer them at the end. And now that's all from my side for the moment. I'm happy to hand over to Christian Blakely, our head of AI at PwC.
Okay, thanks for the introduction and welcome everyone. I'm actually very excited to present this to you today because this is kind of a new field that I've been working on the past several years, and I've brought into PwC Switzerland, and I'd like to basically socialize this with you today, just on some various mathematical topics. So there's going to be a little bit of mathematics involved, but not too much. But basically, I just wanted to give you an overview of what is real-time analytics, what is real-time learning and prediction. I'm assuming probably most of you know something about data science, machine learning, maybe very much. Maybe you're specializing in that. And I'd just like to give you an introduction to kind of what is it about? Like what is it different from? How is it different from traditional machine learning? And I'm going to show probably about 15 minutes of just background information and theory. And then I'll go, I'll launch directly into applications and how we're using it in the field around Switzerland and Europe. So just a little bit of background about myself. I come from the US, obviously. You can tell I'm not Swiss. I'm from California originally. Did my PhD in computational science. Then worked 6 years, started my career 6 years at NASA Goddard Space Flight Center. Then transitioned more into economics and finance, and then came to Switzerland after I wrote a software several years ago, mainly dealing in real-time analytics and in markets, in forex trading and stuff like that. Then I decided to expand more into other areas like defense and now I'm leading the artificial intelligence efforts within PwC Switzerland. So I'll go a little bit over about how we're using that exactly, and because it's actually very exciting stuff. It gives me a chance to build use cases. I'm working right now in looking at anomaly detection in molecules, for example, in the pharma industry. I'm working with defense as well, looking at anomaly detection in defense, working in real-time analytics and market abuse, financial market abuse. So tons of topics, very interesting stuff. So I'll show you a little bit about how we're using that. And then obviously, it's open for questions. I would love to hear from you as well. So let me just dive right in. I'm going to go briefly over a little bit of an intro into the mathematics and what is real-time learning. And then we can get right onto the demo. So basically, what is real-time learning? I mean, if you know machine learning methodologies, you know that what you're trying to do is come up with building patterns, right, in your data and making predictions about them, right? So typically you do this where you have a lot of batches and then you learn something about it and then you make predictions, right? So where in real-time learning, it's not so focused on batches. What you're trying to do is learn from one observation at a time. And so that you're getting streaming information and you already want to make some prediction, already maybe just with one observation. So the focus is really on how to build models such that you can make such inference after just maybe one observation, right? So we're really talking about where you're getting data sequentially in time and you want to already make judgments about that data in real time. So what's nice about it is that it suits data that the data regime might change over time, right? So you might have anomalies that are different, than before, and also the learning and prediction could be done locally too. So, for example, if you're running something, if you're working with a lot of companies who have sensitive data, typically they don't want their data on the cloud, right? You don't want their data on AWS or Google Cloud. So a lot of the times actually you have to work locally just with maybe a Raspberry Pi or something like that, or a local data setup. And another thing about it too is I'll talk about in a second, we're learning both temporally, so we're learning structures in time, but also in spatial dimensions as well. So And then, so anyways, just to give you a little bit more background on this, I actually wrote a software for doing a lot of real-time analytics that we're using right now with PwC Switzerland. Most of the stuff we're using with clients as well. But just to give you an idea, so the methodology learns from streaming data. And what usually typically, as I'll talk about this in a second, but typically when you're doing stuff in real time, you don't have time to make derivatives. You don't have time to do back propagation. You don't have time to optimize over parameterizations, and you don't have time to do with large matrix operations, right? So it requires a different formulation of how you work with your data, and I'll talk about that in a minute. And it's highly adaptable to many ranges of problems. So as I mentioned, I'm using this in anomaly detection, time series classification. I'm working with molecules. I'm working with financial data. I'm working with all different types of data. So it's not just for time series, or it's not just for images, for example. And it's very fast too. So you'll see it's extremely quick to already make predictions about data very quickly. And it's self-contained, so there's no optimization, doesn't need linear algebra libraries. It's very much centered around containing all the information you need in one package. So just to give you an overview, typically, I mean, if you know about, I mean, obviously you probably know about deep learning, machine learning, these types of things. Typically, the structure, if you look at the top there, that's kind of the structure, the overall architecture. I mean, there's a lot of more nuances depending on the methodology, but typically you have your data source, your data storage. You're breaking that up into batches. Kind of that's what I have right here. This kind of in the middle there, breaking up into batches, and then learning something about the data with high amounts of degrees of freedom, right? So the connect, if you're working with like deep neural networks, CNNs, these connections are really dense, right? I mean, you can do, dropout, and there's techniques for regularization, but typically the connections are very dense. And that requires just a lot of GPU power, for example. So you need to learn this in batches, and then you output to a model. It computes some kind of error. You have a distance metric defined. So depending on the problem, you have different types of distance metrics. You back propagate the error back into the network, and then you just relearn that. So this, I would say, covers most machine learning methodologies out there, right? I mean, there's a lot of variations depending on what you're doing, but typically that's it. Now, in the second type, so we look on the bottom there. In real-time learning, you don't have time to do all this back propagation, so you need something else, right? So we have our streaming data sources, and then we have what's called a pre-encoder. What this pre-encoder is it's a fast way of encoding real information into some kind of encoded system that we can work with much faster, right? And I'll go over an example of that. But now you have a pre-encoded system, and that's deterministic. It's not something you learn. I mean, it can be learned, but let's assume it's deterministic. Now you have a step where you're doing iterative sparse encoding. What that means is you're taking the encoded information and you're learning from that iteratively per observation that you get. And typically this iterative process is very quick. So it's almost a linear process, but you're learning something from from this encoding. And I'll go over information on how that goes. I'll go more depth into what that looks like. And then you have your real-time prediction. So you go from your streaming data source, this encoding step, and then you already get your prediction. So just with one observation, I can already start to make a prediction, which is very powerful. I don't need batches of training data. I don't need to run this through with 10,000 times with various parameters. It already starts working with one observation. So that's kind of the overview of there. There's a lot of different flavors of real-time real-time learning. This is just one that I'm presenting today. There's others out there, but just to suffice it to say, this is what I'm going to be focusing on right now. As I'll talk about, this is based on sparse distributed representation. So when I'm talking about this encoding, you get, this is based on sparse distributed representations, because you basically want your data to be sparse at the end of the day. There's a lot of approaches out there that have been worked on in the past. Is hierarchical temporal memory. You might have heard about that. It's a pretty nice representation of data in the sparse world. There's cortical learning algorithm. It's kind of an algorithm on top of the HTM. There's the Feynman machine. It's a nice way for learning in dynamical systems, representing dynamical systems, and then yeah, there's lots of different flavors of these things. So this stuff isn't completely new. There's a history there, but it's very, you don't see it as much as you're going to see deep learning, and other machine learning methodologies. But just to be clear that there's a history here, and you can see some of these references there. So some of the advantages, I mean, you might be asking, well, why would I want to use this, kind of methodology? Well, it actually can outperform, your standard recurrent neural networks, LSTMs, all these flavors. So it's been benchmarked on there as compared. You have, you have in machine learning methodology, you typically need this regularization, right? Because it's too easy to overfit with machine learning. I mean, you get enough data and enough hyperparameter tuning, you can fit an elephant, right? So it's really, you need a lot of regularization. How you tune that regularization, it can be complex. So I just want to be clear that there's just a lot of information from the dense representation that you have to do in order to get to a good model. It's also sparsity, as you'll see, sparse representations are very immune to noise. So it's nice if there's noise, if you're getting noise in your data, say measurement error, some attribution to noise, it can be very immune to noise. So it's a nice benefit. And also these things can run, as I mentioned, these things can run on, anything as small as a Raspberry Pi, an embedded system. They're so great for IoT. You don't need massive amounts of GPUs to do something, So it's very beneficial that way as well. But also there's some disadvantages. Obviously, deep learning methods will still be state of the art for image classification, segmentation, captioning, all these things. You're working with images, you're working with generative adversarial networks. I mean, those are going to be your state of the art there. We can't get around that. But if you're looking for more real-time stuff, the problems that really matter, I mean, to be honest with you, these, GANs and all that, it's great for art. You'll never compete in the art world with GANs, right? It's nice to be able to, do deep fakes and all that stuff. But when you're really working on the client side, when you're really working on problems that matter, none of that stuff matters anymore. You're really focused on these problems that I've come up with. So just keep that in mind. And so with these disadvantages there, I can now go in more into the formulation. So we have the sparse distributed representation. What we're typically doing is we're taking our real world data, and we're putting that into a sparse distributed representation. What is that exactly? It looks just like this. It's actually just a bundled representation, a bundled matrix of one-hot vectors. So basically what that means is collection on you have your basically, you can look at it as a height and a width, and in that direction you have a one-hot encoded vector. So only so in that vector, only one value is 1, the rest are 0. So you can also represent this as a matrix of integers as well, where the integer tells you which value is non-zero. So very simple to work with. You can capture virtually anything. You capture image from images. You can encode images. You can encode the human genome. Whatever you want, you can encode into this structure. Now, I talked about encoding. How this method works is a sequence of encoders and decoders. So when I talk about encoders and decoders, it's very simple. It's just basically a map that takes data, real data, into a discrete sparse representation with some arbitrary number of parameters. You have to choose, your height and your width, but those are the parameters to involve, right? To be involved with. So the decoder is the inverse of that. A lot of the times decoders can be perfect. So you can get a perfect representation, a perfect encoding of data to the encoded world and then back, right? So you can go back and forth sometimes without loss of information. A lot of the times it's not available though, right? So if you're working with continuous data, images, it's not possible. But it's still, you can still approximate it pretty well. Most of the time, I mean, if you're working with anything with images, typically a lot of the time it's not going to be perfect representation. When you're compressing information to a JPEG, for example, you're losing information, but still it's not noticeable, right? You never really, unless you're encoding that information to a very small representation, you're not going to lose that much, visually, right? So a lot of the times that's not a big problem. So that's on encoders and decoders. So just to get that out there, that it's just a sequence of encoders and decoders. Now it gets a little bit more. So there's a little bit more involved now, because what the methodology is, it's a stacked layer of encoders and decoders. That's basically the network. So you could think of this like a neural network if you want, but instead of putting data through a collection of dense connections with weights, what we're doing is we're encoding our information at time. Let's say we have an observation x of t at time t. We're encoding this information into the sparse representation. We're creating a hidden state. That hidden state is in that sparse representation. That then gets encoded more into another representation that's even more refined. So as you're going up these layers from a hidden state to an encoding state to another hidden state, as you're going up this hierarchy, what you're doing is you're extracting the most relevant features from that observation. So you're representing your data at its most fine detail. So you could think of it like like some kind of dimension reduction, if you like. But at the end, so when you're at this top layer, you're dealing with the most valued information that you're putting in there. You're dealing with basically the cream of the crop of your information. That thing gets decoded back into your normal to your real world representation, right? And during this decoding, what you're doing is you're adding your hidden state with your decoded state from the next layer. And what you're trying to learn here is basically at each step, what you're trying to learn is how my information went from this state to this state and back. So that's basically what you're trying to learn. And as you get more data, this becomes more smart, right? It becomes smarter. More smart. I don't think that's an English way of saying that. So, anyways, yeah, it gets smarter as it goes along. So you get more information. You get to encode that information up here. You get to find out what is really the value of my data. You decode that back, and it gives you the prediction automatically. That's kind of how that works. And then the encoding, how do you actually do this iterative sparse encoding to get these hidden representations? It's actually just really simple. You just define a residual error, and then you reconstruct your original data through what's called a reconstruction dictionary. So what that looks like, it's just this iterative sparse encoding algorithm. It's actually been around for quite a while. It's just basically finding out when I apply this dictionary of weights, which are the most relevant features on the output, and then I one-hot encode them. So I look at the maximal weight that is in one column. So it's going to be continuous weights every column. I just take the maximum one. And then I one-hot encode that. So I say that's a 1, I put the rest as 0. And then I reconstruct that. So as I do this, let's say like 3 or 4 times, I mean, this is a very fast operation. It takes, I mean, it's trivial. But if I do this enough times, I can actually reconstruct anything just from a few observations. I can reconstruct an image. I can reconstruct, any kind of data I want. While I'm learning this, I update my dictionary. So when updating the dictionary means I'm learning which of the most relevant features in general are attributed to my data, and I put that information into my dictionary. And this alpha here, it's just a learning rate hyperparameter. It's just a standard. The higher it is, the faster it learns, but usually the more noise that it would allow. So finding this hyperparameter there, that's typically the only thing you have to really tweak. But typically, if you set that to say 0.001, something like that, that's usually enough. So for the prediction and learning, so predicting the next step is basically just this application. You put your data through this network, to this hierarchy, and you get back your prediction, right? But obviously there's an error there. So your real x of t plus 1 is going to differ from your prediction of x of t plus 1. So so what are you doing there? You're just trying to find what that error is and then encode that information back in. And that's typically the setup. I'm not going to go too over the details of this algorithm because I wanted to save plenty of time for some to show you some experiments. But suffice to say, that's the setup. And you also want to learn in time, right? So typically, what you do is you map dependencies to these layers, right? So the dependency layers would look like this. When you're learning, you're typically passing information up the layers to previous layers. So what it's doing is it's learning in time as well. It's learning what are the most relevant features. You could think of this if you've worked with LSTMs, for example. If you've worked with it's called clockwork LSTMs, where you're passing information back to previous temporal lags. So layer number 4, its most relevant information will be passed to layer 3 from the previous time steps, and etc. So you're learning not only in the spatial features from the encoding, but also back in time. Yeah, so typically, a model, a pipeline model would work like this. You have your real data down here. You put in your images or your time series observations. You also can encode labels if you have labels. So if you are trying to predict a label for classify a time series or classify an image, you'd put that label in a sequence of images you would classify that you would classify with, you would put the label in there. That encodes it to this sparse distributed representation. You then get your layers, and then you do the sparse encoding and the predictive into the predictive hierarchical layers with this memory system, and you get back your predictions at every step, and then you decode that back into the real world. So you put in an image, you have a sequence of images, you put this in there, and what you get is the prediction on the next image, what the next image would be. So if you have a video, for example, you want to predict what the next sequence in the video would be, you would have a representation of that image in this sparse world. You decode that back, and then you take the error and you encode that error back through here. That's typically the setup, but now I wanted to, with the time I have left, I just wanted to go over. So I have some examples with benchmarking with RNNs, for example. Yeah, I'm going to go over this right now. I'm going to show some examples. So while I have a little bit of time left, I'm going to show you. I have so most of the stuff I mean, most of you probably, I don't know, you might use, I assume you might use Python for a lot of your work. Python seems to be the go-to language. I'm a Java fan. I really like Java, and what I typically like to do with Java is write these I would say user interfaces, right? So because a lot of the time in real-time analytics, you need to show stuff in real time, and with Python, that's much more difficult. Just because there's a lag between the language itself and any type of language outputs, right? Graphical outputs. So just to show you an example here of what I mean. So what I'm going to do is I'm going to show 3 time series, and these time series, they have outliers. Well, 2 of them do. And what it's going to do is going to learn these time series in real time. And it's going to predict 1 step ahead, but also just learn, so it knows nothing about these time series at all. So my approximations are going to be very bad. My predictions are going to be very bad at first, but over time, as you'll see. Now, there's going to be a lag on your screen probably. On my screen, obviously, it's doing everything much faster in real time, but just because of the video transfer, you're seeing it looks like there's a massive lag, but trust me, it's very fast. I'm just going to run through this. You'll start to see that my learning, the time series that I'm predicting, they will start to converge to my predictions. So already that sine auto wave, it's pretty much already learned. Now you'll see here in a second how other waveforms have been learned. And over here on the left, this right here, this is showing that representation of my data into that encoded space, right? That hierarchy, that sparse distributed representation. So I'm basically encoding this information into here, and that's what you're seeing. And so it's learning. It's not learning from the time series itself. It's learning from this encoded state. But so just as this is learning, you're going to see. So what's going to happen is that when these start to converge, it's going to start to predict the outliers. So already you can see that that the two of the time series are starting to converge. It's starting to catch up on the green one. Obviously, in real time, this learns probably after about 4,000, 5,000 observations. But this is just to give you a sense of how it's learning. So already you can see that things are starting to converge, and you get your predictions right away. And then you can obviously stop learning and just start to make predictions right away. So oops, I messed that up. Well, anyways, I just wanted to give you an intro to that, and also there's a lot of other things that real-time learning can do besides just learning time series. So let me show you another example with another software I wrote here. So we can also look at, say, for example, protein data, and this is an example of drug experiments on mice, and there were about 100 mice that had Down syndrome and 100 that did not, and we want to determine from their protein biomarkers which mice had which mice had Down syndrome. And so it's just basically learning just from the protein biomarkers. So so here what I'm going to do is I'm going to show you some ways that we can determine which mice had Down syndrome. Now, so just to give you an idea, what I'm going to do, I just upload, these are the protein biomarkers right here. And each protein biomarker has a representation and some normalized representation on the real line. And what I want to do is I want to show you a couple of ways how we can do local interpretability and global interpretability of the predictions, right? So because a lot of the time in machine learning we talk about black boxes and interpretability. So the methodology actually also happens to be very interpretable. So here I'm learning in real time all the protein biomarkers of all the mice, and you see how it updates all the information that I need. I get that in real time, and basically I can just play around with my parameters to get a representation of how I want to predict if I'm given data on a mouse, how can I determine if they have Down syndrome? So a lot of the times it's just basically playing around with the number of training rounds, the number of training test splits, stuff like that. But just to give you an idea, I'll train it. So right now it's saying, it gives me my global interpretability is saying that, this protein biomarker is the most influential to making an impact on my prediction for if they, had Down syndrome or not. Now I can look at my data. So I've built a few different data viewers, And one of them is called, it's a contrastive approach to learning about those features. And what that is I'm projecting all the information into 3 dimensions. So this is the projection of the mice. I'm just using PCA here, where the pink ones have Down syndrome and the blue ones do not, from their protein biomarkers. Now, just if I didn't know that the labels actually, which ones had Down syndrome or not, how would I conclude which ones did and which ones not? It'd be very hard just from this, right? But so this methodology that I built, actually I can influence how I pull information by what's called this contrastive approach to PCA. So what I'm doing is I'm projecting all that information into a space where I'm taking out certain representations of the protein biomarkers from my test from a control set. And what I get is this more of this representation. And from this representation, it's much more clear. This cluster right here are all the mice that did not have Down syndrome. The ones out here are the ones that did. Now I can determine which ones. I can look at my prediction. I'm sorry. So these are the ones that do have Down syndrome. These are the green ones do not. But I can put my mouse over a certain mouse, and it will give me a reason codes as to why that mouse was predicted had predicted to have Down syndrome. It gives me the reason codes. What are the most impactful proteins? So this just gives a user a way to basically look at their data. You can do this in real time, so you're learning in real time. I don't require big Python packages. So I'm doing this all just with native Java code. So it just gives you an overview of how you can do not only real-time learning, but also interpret your results afterwards, because that's typically very important when you're working with clients. So yeah, there's hundreds of more use cases I could show you, but we're running out of time. I also work with in AI and music, so learning music in real time. I have a YouTube channel where I showcase some of this stuff. It's called Zero River Pianist, if you're interested. I have a lot of more examples on my YouTube channel, just to give you an overview. But this is typically what we're doing, stuff like this, very creative ways of representing data, doing real-time learning, not just using standard pedestrian machine learning approaches. Is really about, because when you're working in the market, typically you're working on problems that have never been looked at before, and it takes a large amount of creativity. You have to be creative with stuff. It's no longer about Python and Jupyter notebooks, and it's really about being creative and finding unique ways of representing data and finding anomalies in that data. So with that, that was just a brief introduction, but I'm out of time. But now it's the Q&A session. So happy to answer any questions. And also, if you want to reach out to me, christian.blakely at PwC.com. Feel free. Happy to discuss more. If you want to grab a coffee sometime while social distancing, no problem. We can do that. Anyways, back to you.
Perfect. Thank you very much, Christian, for this interesting presentation. Now we're coming to the questions. We already got some, but still use the chance to insert your questions here in the chat window. So Felix is asking, you mentioned you work with molecules. How does this type of data relate to time series?
Yeah, great question. So molecules, typically what happens in the drug industry when you're looking at how a drug is developed, you start with lots of different representations of lots of different possible molecules. And what you're doing is you are doing tests on these molecules, right? Experiments. So looking at different factors like toxicity, solubility. These experiments go through time. Right. So you're looking in the time domain, what are the most impactful features, right, from the experimentation. So it really is a time series problem at the end of the day. But the molecules itself, they're the representation, and what you're trying to do is find the anomaly out of all those molecules. You're working with 40, 50 molecules. You want to find what representation is the one that's going to cure cancer.
Perfect. Thank you very much. Nicholas wants to know, are you adjusting the mapping settings in regard to the industry you are working for?
Yeah, so yeah, everything is adjusted for the data at hand. We typically, before beginning the engagement, we never see the data beforehand. So a lot of the stuff is privatized. A lot of the stuff is very secure, and obviously very yeah, they don't allow data to leave their headquarters. So once we're on site, we adjust everything according to their data. We have a setup repository. We begin with that. We begin with the data, simple data exploration. Simple data science steps at first, and then we adjust things to the model over time. And then real-time systems can be built once we know what the data looks like.
Mm-hmm. Then just at the start, Mustafa asked, is there for a pre-encoder is there for the pre-encoder a pre-trained model trained on data from the past?
Nope. So all you need to know are the dimensions of the data, the dimensionalities of the data. Once you have the dimensionalities of the data, the ranges, important ranges, I would say, then you can start your encoding. So the encoding usually is pretty simple at that point once you know your dimensions of the data you're working with.
Mm-hmm. Then we were coming more to a career topic. Nicholas is asking, how does a typical day look like when you're starting as a junior at PwC?
Yeah, great question. So typically, when we onboard people, I mean, we make sure, of course, that they're passionate about data science and they're passionate about challenging problems that they've never seen before. That's the first thing. The second thing is then we try to get them on board with internal topics. So we have a lot of innovation problems, topics that we are working with in the field, building assets, building pipelines and machine learning technologies for clients in the future. So typically we like to just get them their feet wet with helping out building the innovation first. Obviously here this requires technologies such as I use Java, but most of my team is using Python. That's fine too. I'm not a huge, I don't really care that much about languages, but typically starting out with internal innovation projects, and then we'd like to get them once they're moving up after maybe say a year, get them out in the market working on client projects, maybe 50 to 60, 80% of the time, because it's a lot different when you're working on the client side. Different environment, different people, different cafeterias, different food, different problems, different data. So we like to get them out there as quickly as possible.
Mm-hmm. And then Julia is also asking which technical skills are most valuable for junior position candidates.
I would say statistics is huge. Probability. If you know really good statistics, probability, like that is the best thing. Because I mean, a lot of the times looking at data requires a lot of statistics. Secondly, I would say programming skills are really good too, especially Java. And not Java, but object-oriented languages are nice as well. Python is good too. Obviously, if you're good with all the standard machine learning technologies in Python. But I would say really focus as much as you can on statistics, probabilistic models. Those are huge. People tend to think that statistics and probability are boring topics from like the 1970s, whatever. But actually, I think they're some of the most fascinating, most interesting, and will get you further in your career than just basic, data science.
Mm-hmm. Thank you for these valuable tips. Then Kaxin want to know, how is the real-time analytics relevant with PwC's business?
Yep. So great question again. So PwC's core business doesn't necessarily have any relevant use cases, but we are working, obviously, as you might know now, we're working all over the place. As I mentioned, pharma, we're working with on the financial side. We work with banks. We work on the financial exchange. I'm working right now on the financial exchange. So this is typically a very nuanced subject, and we're trying to drive analytics with these companies because PwC can't survive forever on audit. So I need to be clear that PwC is not just an auditing firm, but now we've really driven up, I think, one of the most competitive practices in data analytics out there. Obviously, we can't compete with Facebook and Google and Amazon on the technology and the GPUs and that kind of thing. But for the problems that really matter in the market, I think PwC is we're trying to lead them. We're trying to lead it as one of the best.
Mm-hmm. Great. And what do you think is the future of real-time learning? What's the next big thing coming?
Yeah, another great question. So my hunch is that this is going to be big on embedded systems. So when you have real-time learning in your automobile, when you have real-time learning just virtually anywhere, it can learn from nuances in your data. It can learn from anomalies. So IoT. It's a big one. The reason being is that this stuff is very fast. You don't require GPUs. A lot of machine learning productionization. You have to do stuff on GPUs, and then you encode that. You embed that into some system, but it can't deal with a lot of new data that it hasn't seen before, right? So typically, it always needs to learn on some cloud. But a lot of the places that you're working at, they don't want their data on a cloud, so you have to learn locally. So real-time analytics could be looking at real-time healthcare. So I'm working also in real-time predictive healthcare, understanding information from the brain, for example, with EEGs. I'm working with a couple companies of biohealth sensors. I'm working financial indicators, obviously EEG. I work with defining, how to help patients who are in comatose, how to recover. Geographical monitoring. I mean, there's lots of use cases for real-time learning that go beyond just standard Python machine learning and deep learning.
Mm-hmm. And then coming back to audit, Julia is asking if we also use real-time learning for audit, and if yes, how?
Yeah, great question. Real-time audit. Yeah, that'd be fun. So it's not really. I would say that the applications there are not as I would say useful because of the fact that audit takes just a massive amount of um, other steps in order to really solve. We work with internal audit though. We work with companies in their internal audit and to define anomalies. And there we use all types of machine learning. So we use Python. I have a colleague working with companies on internal audit. Dealing with detecting anomalies in report in payroll, for example. So so a lot of the stuff, I would say real-time analytics is not really applicable in audit. I mean, it can be used, but still there's just other great things out there that can be used, not just real-time learning.
Perfect. Thank you very much. Is there another question? If yes, it's the last chance to ask. Otherwise, we will soon close the session. Wait a minute. Good. As nothing is coming at the moment, I would say we're closing here. Thank you very much, Christian, on your side for the interesting insights. And thank you to all participants for joining us for this webcast. And if you have any further questions, drop us a message. And yeah, we're definitely hoping and looking forward to seeing you soon. And enjoy your afternoon and have a great time. Bye-bye.
Thank you. Bye, everyone.
Bye.